All right, folks, Bass Action is back in action here. On this page of notes, we are going to take a look at how to find domain algebraically. In your previous courses, you would have only done that graphically. And on example 2, we are going to look at some of our function operations. Let's start with finding domain. The general idea of finding domain is we want to find the places where the function is will work. That's kind of the phrase that people really like to use. But in other words, what we're looking for, a better way to think about it, is what we have here, and that's we want to find what we call domain restrictions, or in other words, where are places where the function is not defined. Okay, so we're going to have three main categories that we need to consider, and if you want to pause this and write them down, we're going to have fractions, we're going to have even roots, and we're going to have logarithms. So each of those are going to come with their own type of a restriction. So when we think about fractions, our concern on a fraction is that we might have a 0 in the denominator. We know that that's not allowed. Okay, so we're going to have to figure out where any of our denominators would become 0 and exclude those values from the domain of all real numbers. For our even roots, our concern is that we would have a negative radicand. Now, the radicand is just a fancy way of saying the number underneath the radical. And we're most specifically concerned with the even roots. Okay, odd roots won't cause a problem for us, just the even roots. Logarithms are actually going to take both of these ideas into effect, and on a logarithm, we cannot have a 0 or a negative argument. Now, we're not going to cover the logarithms too much right now, but we will definitely come back to them later in this semester, and you certainly worked with logarithms in your last class. So in this first part, we're just going to focus on fractions and even roots, and we start out with the assumption that the function has all real numbers as the domain, that everything is allowed, and then we will begin to eliminate from there and move forward. So, for example, on example 1a here, what I can see is that I have a fraction. So my only concern about this particular problem is where this denominator might become 0. So the first thing that I'm going to do is I'm going to factor this denominator. So I can go ahead and I can factor this pretty easily, and I get an x minus 5 and an x plus 3. Now, thinking about my zero product property, then I understand that this denominator would become 0 at a negative 3 and at a positive 5. So I can go ahead and I can put those numbers on the number line. So I can draw a little number line here, and I think it's good to visualize these on the number line. It'll help us as we move forward. So I have a negative 3 and a positive 5. Now, those are values that would actually make this fraction, the denominator of this fraction, 0. So I'm going to give myself some open circles there because I need to exclude those from this domain of negative infinity to positive infinity. Every other number along this number line, will give me a non-zero denominator. So those are all acceptable. So I have two choices on how to write the domain for this function. The first one can be written in what we would call set notation. So I would say x such that vertical bar is read such that, or as long as x is not equal to a negative 3 or a positive 5. And we can do our little curly brackets. Set notation is going to be the easiest when we just want to exclude some single locations. I could write this in interval notation, in which case I would need to write an interval for all three parts on the number line here. So I would write negative infinity to a negative 3, parentheses, union. Then I'd write the next interval, negative 3 to 5, parenthesis, union, and then my last interval, 5 to positive infinity. Certainly, I think that that's a much busier type of notation for this domain, but it would be acceptable. Now let's move on to the next problem. On our next problem, I can see that I'm working with an even root. So remember, up here on the top, my even root, my concern is that I would have a negative radicand. In other words, I'm concerned that this part right here under the radical could potentially become negative. So what I want to remember is that 0 is my boundary between positive and negative. So the first thing that I'm going to do is I'm going to factor this. So I'll have my x minus 5. It's the same numbers from the last problem, x plus 3. And I can put those numbers on the number line again. Put those on the number line just like I did before, negative 3, positive 5. Now remember, with my even roots, looking back up here at the top, my even roots, I'm only worried about them becoming negative. I'm not worried about them being 0. So this time, I can, instead of putting open circles, I can put solid dots there because negative 3 and positive 5 are acceptable this time. Now what I want to figure out is somewhere in one of these intervals, or possibly two of these intervals, my values under my radicand are going to become negative. So we're going to actually choose some numbers and test them. So if I pick a value, for example, from this interval, and I plug a number from this interval into either my non-factored form or my factored form, I will determine, just pick, let's say, negative 4, and I would do it mentally. So for example, negative 4 minus 5 is going to be a negative number, and my negative 4 plus 3 is another negative. So I would have a negative times a negative, and that's positive, which means every number in this interval would be a positive number, so that interval would be acceptable. If I pick a number in this interval, my easiest number would be 0. If I plug 0, let's think about this form, into my non-factored form, I can see that I would get a negative 15, which means this entire interval has to be rejected. Now, it should follow a pattern. If this one works and this one fails, then this one should work. And we can test that. We could put a 6 in here, and we would find that we would get a positive times a positive, so this would be positive. So in other words, this interval is okay. So now we're actually going to describe each of these acceptable intervals as our domain. We have removed certain sections where the function becomes undefined, and that's our middle section. So our final answer here, we're going to write in our interval notation, negative infinity to negative 3, parentheses on the negative infinity, but a bracket this time on the negative 3 because of this solid dot. Continuing on, union, square bracket for the 5, positive infinity with the parenthesis. So there's my domain for that problem. My last problem that I'm going to be looking at combines our two ideas of a fraction and an even root, our fractions and roots. And now I have, again, I have both a fraction and a radical. This time I need this radicand not only to stay positive, but I need to eliminate where it becomes 0 because the 0 would make my fraction undefined. So we can repeat this process, very many of all the same numbers. We're just going to analyze it slightly differently. So I still have the x minus 5. I still have the x plus 3. I can still stick those on my number line, my negative 3 and my positive 5. But this time, combining the two previous problems, I need these to be open circles because those values would make the denominator of the fraction 0. Then I would test each of the intervals just like I did in example B, and I would find that the radicand remained positive in these outer intervals, and the radicand became negative in the middle interval. So my final domain, I always like to put these infinities on here, will be negative infinity to negative 3, and this time I'm going to use all curved parentheses, 5 to positive infinity. So there's my other domain. So those are going to be my domain problems, and we are going to explore this much more in class, but this is a good start to the process. Now let's take a look at, totally switching gears, we'll look at some function operations. So our first problem that we have here is leading us towards some processes that we're going to do in our next section. So we are going to evaluate our function at 2. We're going to evaluate the function at 0, and then the denominator is just going to be 2 minus 0. So I'm just going to take that 2 and I'm going to plug it into my actual function that I have up here, this f of x. So my f of 2 would give me, just showing all my steps. All right, so we've substituted in on these initial parts. And then we can continue, and this is all going to be over our 2 minus 0. So cleaning this up, we're going to have our 2 over a 1 there. So that one's going to clean up pretty easily to a nice 2. Of course, 0 over anything is going to be 0. So we have a 2 minus 0 over a 2. That simplifies to a 1. So all that work just to get the 1. And that's okay. Moving on to the next one, we are going to substitute a negative x into both places of x into this problem to our original function. So we're going to have a negative x all over a negative x minus 1. And you actually could have this as an acceptable answer. Now, the important thing to recognize is that your textbook is often going to factor out the negative from this denominator and is going to clean this problem up just a little bit. And they're going to write it like this. So they're going to factor that negative out, and they're going to get an x plus 1 in the denominator. Then they're going to recognize that these two negatives will cancel each other out and create a positive. So this same problem could be written as an answer that looks like this. Now, either one is acceptable, but it's important to recognize that these are in fact the same. So you might have one and your textbook has the other, and you need to recognize them as equivalent. On the next problem, we're going to take 2x plus 1 and we're going to substitute it in each place for x. So we're going to have our 2x plus 1 over 2x plus 1 and then minus the original 1 from the problem. So this is going to simplify to 2x plus 1 all over a 2x. Our next problem is going to get, or our last problem is going to get a little bit messy, but this is going to help us with our next lesson. We're going to do 2 different operations here. We're going to replace x with an x plus h, and then we're going to subtract the entire original function. So this is going to get kind of crazy. So working with our first function here, we're going to have our x plus h all over our x plus h minus 1, and then we're going to subtract the original function of x over x minus 1. I'm going to erase this here. Small little spot there, sorry about that. Then we're going to get our common denominators. So our first fraction is going to be multiplied top and bottom by an x minus 1. And we can think of this numerator as a nice binomial. That'll be helpful for us. Our second fraction is going to be multiplied top and bottom by the denominator of the first. So x plus 1, or x plus h minus 1 all over x plus h minus 1. Now, in our first fraction, we're going to FOIL these two terms. So we'll have an x squared, and we'll have a minus x, just foiling these, plus an xh, minus an h. The other thing I like to do is I like to change this to a plus, and I like to put that negative right there. It's going to help me when I go to distribute this x to each of these terms. So next we'll have a negative x squared minus an xh plus an x. And this is all over an x minus 1 and an x plus h minus 1. Don't need to FOIL that out. Now, we're going to have some things that are going to clean up very quickly. Our x squareds are going to cancel. Our minus x and our plus x will cancel. Our xh and our minus xh will cancel. And we're left with just a negative h. So our final answer can be written as a negative h all over x minus 1 times x plus h minus 1. This looks like a weird answer. It doesn't seem particularly useful for us right now. However, this is going to be a little bit of a preview for us for our difference quotient that we're going to do in a few lessons. And this will help you later with limits when you get to your calculus classes. So that's all that I have for now. Just make sure you can follow these steps and we'll extend it some more in the next lesson.